Hello and welcome to today's episode of Deconstructing CDK patterns. And the pattern we're going to be talking about today is the scalable webhook. This is designed to introduce a level of resiliency into your application, especially when you have serverless components talking to something that isn't serverless, say RDS. So stay tuned to find out more. I found this pattern through the serverless hero that is Jeremy Daley. If you don't follow him on Twitter already, I would advise you do and check out his newsletter. But I found this pattern on jeremydaily.com and he has this one as well as a bunch of others, so please go check it out. Before we go any further, I just wanted to talk about AWS scaling and limits because it's something that I was especially guilty of whenever I first moved to AWS. I tended to think that because I was on the cloud and because everybody keeps using the words infinitely scalable, that meant that if infinity customer requests came into an API gateway, that it could route them to an infinitely scalable number of lambdas that could then interact in an infinite level of Dynamo DB operations. But that just isn't true. And it's not true for very good reasons. Amazon introduces both account level and component level limits on everything in AWS. And the reason why is because if one customer could scale any individual component infinitely, it doesn't matter how much hardware Amazon provisions, one person could take down the whole cloud. So these are here so that if you have a limit on, say, the number of requests on API Gateway, if you want to go much bigger than the default, you can ask and that's okay, but it allows Amazon to provision the amount of hardware for you. So looking into the API Gateway then, you actually need to know how many API gateways are in your AWS account to understand what the amount of requests are that you can receive. And you'll learn the deeper you get into AWS, account strategy is massive. Mono accounts, which have been popular since the start of AWS, you learn very quickly you run out of limits so fast. And that's why whenever we see here 10,000 requests per second per account, that means that if you have 100 API gateways in this account and each of them get an even amount of requests, you can have 100 requests per second per gateway in that account. It starts to diminish really rapidly. And even with that, so the 5,000 burst, what that means is you can have 5,000 requests hit it at the exact same millisecond. But if you get 5,001, the one will get rejected as too many requests. So it's not 10,000 requests can hit it instantly, and then the rest of the second nothing happens, and then 10,000 can hit it instantly. It's a case of 5,000 can hit it instantly, then a break, then 5,000 more, or 10,000 distributed evenly over the second. It's quite confusing to get your head around, but it is a really important concept to understand. After that, Lambda functions themselves, you need to know how many lambdas are in your account. And not only how many lambdas are in the account, but what level of scalability do all of those lambdas have. So if you've got a mono account again with 1,000 lambdas in it, and one of those lambdas is sitting on 600 concurrent executions, well, you've actually only got 400 left in your account concurrency. So all of your lambdas can't go at the same time. So this is really important to know. Again, break up accounts on a bounded context and it gets simpler. But if you want to do one big account, well, that 1,000 runs out really fast. Finally, our database in this scenario is Dynamo DB. Now, Dynamo is designed to be massively scalable. This, if you read Alex Debris' book, everything that's tier 1 on AWS is running on Dynamo DB. So it's not as much of a concern here, but there is still this limit of 40,000 read-write units. But let's just say you're one of the customers who doesn't use Dynamo DB for everything. What would the scalability of the database look like? Well, if we look at Aurora MySQL, you can see if you pick db.t2.small, the max connections is only 45. And even if you go up to r3.large, that's when we hit 1,000. So there's quite a big window of instances that are way less than our 1,000 Lambda function executions. Now, that means that if we had 1,000 Lambdas, all trying to insert a record into the database at the same time, and we had a T2 small, you're just denial of service attacking your own database because it can only hold so many connections. Then if we look at Postgres, most of these instance sizes are good, but if we look at the bottom one, db.t3.medium, it's 420. So again, it is still possible to cause the same problem with this database setup. This is why the scalable webhook exists. It is introducing a buffer between the requests that come into the API gateway and the database. It's a holding area so that everything doesn't hit the database at once. And in this case, we're using SQS. Now, I can't mention another component without talking about the limits. So if we look at what we can store in SQS, we can have 120,000 in-flight messages and a backlog that is unlimited. So I think this is suitable for the job of slowing down requests between customer and database. To actually slow down the requests then, what we do is we have a throttled lambda subscribe to SQS. What we mean by throttled is we set the concurrency, the maximum concurrency way down. It could be 1. You could be saying, I only want 1 instance of this lambda to ever exist. And then it will just take 1 message off the queue at a time and insert it into the database. It's not going to be fast, but it's going to be reliable. I wanted to mention before going any further, especially now that I've talked about Lambda concurrency and limits, the Lambda function here that sits in between the API gateway and SQS, in this pattern it exists, but in real life you could delete that Lambda and use Apache VTL, and that way you'd have 1 less Lambda, which means less costs and more concurrency for everything else in your account. Now, to talk about the pros and cons of the pattern, I've went pretty deeply into it protects the database limitations and it makes it scalable. But I just wanted to point out, first of all, it protects your wallet. If everything in your account just scaled up instantly to the maximum amount of concurrency, you're paying for that. Whereas if the amount of requests come in and pop a message on SQS, you can have an alarm in there to say, hold on, the load on this service is way higher than normal. And then you can introduce a process that says if you're happy for all of those operations to go ahead, or if there's been some kind of programming error and it's actually a waste of money. The next thing is it protects against unpredictable spikes. Traditionally, what we've done to protect against spikes is you would look at your load and say, okay, how many users are going to hit this service? How much do I need to provision to be able to cope with that? This is the complete opposite, where what you're saying is my database size is X, so how much can it cope with? Okay, well, if 4 times that volume comes in, it doesn't matter. It'll just sit in the queue until it's processed. So that's pretty awesome. But it does come with a couple of cons. First one is you've introduced an eventual consistency model. What I mean by that is there is a gap. So it depends a lot on how many requests come in and how many Lambda functions you have pulling items off the queue. But it is possible that 1,000 requests come in and you just have 1 Lambda subscribing to that queue. It's going to take a while for that item to be inserted into the database. So there's a period of time where the user thinks that they have inserted something into the database, but it's still in the queue. So you need to set those expectations up front. Then the second con is this is for write operations. To protect read operations, you need to look into other things like Elasticache and Redis. Finally, I couldn't talk about this pattern without talking about the new AWS RDS Proxy. So this is a fully managed service built by Amazon to pretty much do a similar thing to the scalable webhook. It's not generally available yet, so that's why this pattern still exists. And it's also only for RDS, whereas you can still scalable webhook onto Dynamo if you want, which is what we do in this pattern. To get the code for this pattern, you can use the cdkp module that's out there on npm. So we can do npx cdkp init the-scalable-webhook, and that will pull down the TypeScript version. If you want the Python CDK version, it's the same command with --lang equals Python on the end. Or if you just want to view the code, walk through it and browse it, you can always go to github.com/cdkpatterns/serverless. So now that we've talked the theory, let's jump over to Cloud9 and do a demo of the code. Okay, first step, we're going to download the code, which as we just saw, we can use this handy command, which creates this scalable webhook folder here up in the top left. And while that's cloning, I'll just walk through some of the features. So we have our main CDK stack inside the lib scalable-webhook stack.ts file. We also have some lambdas inside the lambdas folder. So let me just make this a wee bit smaller. So inside our stack, we have our Dynamo DB table. And all we're doing is we're setting a partition key. We don't have any kind of sort key on this at the minute, but we just have a name of ID. And the reason why we have this is because, as the comment shows on the right, it's to squash duplicate SQS messages. So at this point, I'm going to mention that with SQS, it guarantees to send a message at least once. So you will see throughout this pattern a deduplication ID. Now that that has pulled down, jump into the folder, and as always, I can do npm run test, which will run the unit tests for this pattern. The tests are always found inside the test folder, so you can see them in there. This pattern had 7 tests and they've all passed, so I'm going to go ahead and deploy this before talking through the rest of the code base. So npm run deploy is bundled with every CDK pattern, and that should be the last I need to touch this console. So minimizing that down. So I mentioned the deduplication ID, which we'll get to slightly later on. This is our SQS queue. You can see that there's nothing special configured about it. The only difference is that messages are only staying on this for 5 minutes, but you can configure it for longer. Now we have our publish lambda. This is the lambda that sits in between the API gateway and the SQS queue. So this is what specifically puts items onto that queue. We pass in the queue as an environment variable, and we grant it permission to send messages. So it's inside the lambdas/publish folder. So let's just take a quick look at it. Okay, so this is where we're going to start talking about the deduplication ID, and this is it here. In our message attributes, we're including this parameter called message deduplication ID of type string, and the value is event.path plus a time. So what this pattern is going to do after we deploy it, it's going to stand up an API gateway, and any URL we hit on that API gateway, it is going to insert a row in the Dynamo DB to say hello from and whatever that URL is. So if I hit /YouTube, it's going to say hello from /YouTube, but you got to bear in mind that I said SQS can send multiple of the same message. So we need to account for the fact that I could say hello from YouTube twice intentionally, or SQS could just send the same message twice. So that's why the deduplication ID in this case would be YouTube and then the exact time that the message was sent. So if it sees the same message twice, it's already inserted into Dynamo, so it can ignore it. Whereas if it's 2 different instances of hitting /YouTube, it will insert both. You'll see it whenever I do the live demo. And then there's the message body, which is hello from, and then QURL is just used from our environment variables that we saw a second ago. To send the message, then we can just do sqs.sendMessage, and it's as simple as that. This send response, this is what you will see in the browser whenever I hit the URL in a second. Moving on to our subscribe lambda then. This is the throttled lambda that subscribes to the queue. So the big difference with this one is it has reserved concurrent executions as 2. So there will be 2 and exactly 2 instances of this lambda. We also pass in the SQS queue, and we pass in the Dynamo DB table name. We give it permissions to consume messages from the queue. We tell SQS that this is a Lambda event source, and then we give it permissions to insert information into Dynamo DB. So all of that from line 46 to 58 is setting up a Lambda that can subscribe to an SQS queue and insert into Dynamo DB. If we go and look at the code for that then, so SQS messages get sent as an array, which is why you see this for loop. But all it does is it uses the deduplication ID as the ID field, which if you remember from up here, whenever we defined our partition key, ID is our field. So this means that if we insert a record twice, it will just flatten it. Dynamo DB, if you have a partition key, doesn't let you have duplicate instances of it. So that's how we're getting around duplicate messages. So it uses that deduplication ID as the ID, and then it just inserts message as the payload. And then again, it can just do dynamo.putItem, and it just logs whether it was successful or whether it failed. It doesn't need to take any further action on this. Now, in a production setup, you would want to put up a DLQ, and any of these messages that fail, you would want to have some kind of error hospital flow, and that's what Jeremy describes on his blog, but I didn't include it for the sake of keeping the pattern short. Okay, so we got to this queue, or this Lambda. After that, the only infrastructure we have is our API gateway, and it says that any URL you hit will go through to our publish Lambda. So that's the entire infrastructure. What I'm going to do is go to Dynamo DB. You can see we have our table, and if I go to items, it's currently empty. So if I go back to this endpoint and I just open this, we get that what I showed you earlier. You have added a message to the queue and it gives you the SQS message ID. But if I also add in YouTube, we should now see two records in Dynamo DB, one from just slash and one from YouTube. And there is a delay on this, so it's actually good that we're only seeing the first one at the minute. So you can see hello from slash, and now you see hello from YouTube. Now, to bring up and demonstrate the deduplication ID, if I hit this URL again, I should get a second message. So this is generating another deduplication ID, which has a timestamp off whenever I click that refresh button. So the IDs will be different. It just might take a second to show. Oh, there we go. So now we have two of these, even though the message is the same. We got different IDs based on the timestamp of when it was sent. So that is pretty much how the scalable webhook works. As always, the only thing to remind you before going any further is to delete all your infrastructure that you've deployed to learn how this works. So you can always do npm run cdk destroy, and that will tear down most of the infrastructure, but you need to manually delete your DynamoDB table because CDK by default doesn't delete tables. So hopefully you've enjoyed this, learned something. Hopefully you can subscribe to this YouTube channel, follow me for future videos, and come follow me on Twitter at CDK Patterns. Thanks everyone.